Yeah, thank you for the introduction. So as you said, this is the first of 2 introductory talks meant to bring all workshop participants to the same level, no matter whether you're coming from a mathematical background or more from an applied background. And mine is about the various engineering tricks that are used to make deep learning work in practice, and Philip's will be about understanding why they actually work. And since this is a public lecture, I try to ensure that this also works as a general crash course on deep learning. So who of you has not used deep learning before? Oh, that's just very few. Yeah, that's good because I'm going to go very fast. Okay, so as you see from the title, I'm taking an engineer's perspective here, which means that sometimes I will try to explain things more intuitively and hands-on and not mathematically. So if some of my explanations sound a bit stupid, it may be on purpose. All right, so I will start with going over some example tasks, just to make the main part of the talk less abstract. Then we'll cover the elegant core ideas behind deep learning and machine learning in general. And then we'll have a look at how these ideas are realized in practice. So this looks a little less elegant and more like it was done by engineers. And it may also not be the best solution, but empirically it seems to work quite well. Okay, let's start with the examples. And just to take away the tension, this will neither include killer robots nor Arnold Schwarzenegger, just some narrow AI that focuses on solving some specific single task. So what we can do, for example, is regression, like given the recipe for a concrete cylinder, try to predict what force it can withstand before it bursts. That was just an example I found that has a lot of nonlinear dependencies, so it can be solved by deep learning, maybe. Then we can do binary classification, like distinguishing photographs of chihuahuas and blueberry muffins. It's not very easy.
At what success rate?
I don't know. I don't think anybody has actually done this. Then we can do multi-class or categorical classification, like recognizing digits or object detection with a fixed set of possible answers or classes. And we can do image colorization, creating some plausible version of a gray photograph, a colored version. Then we can do image generation, like creating small photographs of bedrooms that don't actually exist, or album covers. We can also generate text. So this is from a very popular blog post by Andrej Karpathy, who trained the network on different kinds of text. So for example, if you train it on a lot of Shakespeare, then it will learn to write in verses, and it will put a name in front of every paragraph, and the names are also made up. And it sounds a bit Shakespeare-y and pathetic. And if you train the same on Linux source code, on the Linux kernel source code, then it will generate something that looks like C code. It doesn't declare all the variables it's using here, but it also puts in some helpful comments, such as free our user pages pointer to place camera if all dash. And then, since we're going to also talk about audio here, an example from the audio domain is to try and detect where in the music piece there's a transition from one musical part to another, like from the verse to the chorus, or from the chorus to the break, something like that. Okay, let's get to the core ideas behind deep learning, see how these tasks can be solved with deep learning. Or actually, let's first look at how they can be solved with machine learning in general, because that's mostly the same. So the first step when trying to solve something like this with machine learning is to formalize the task in a way that the solution to the task can be expressed as a mathematical function. So we'll go over the examples again to see how this can be done. For the regression task, it's quite easy. If we fix the set of possible ingredients for this recipe, then we can express the recipe as just a list of numbers giving the quantities for each component. And the force that the cylinder can withstand before it bursts is also just a number with some given unit. So we can express the solution as a mapping from an 8-dimensional vector to a scalar that tells how much force the cylinder with this recipe can withstand. For the image classification, for the binary classification tasks, if we fix the size of the input image, then we can express the input as just a matrix of gray values, and the output would be a scalar that between 0 and 1 that gives the muffinness of the image received. So for this input, the output should be 0. Then for a multi-class or categorical classification, it's quite similar. We can again represent the input as a matrix of gray values and have the output be a vector of class probabilities, one probability for each of the 10 possible digits that sum up to 1, like this. So we could also represent it so that the output would be just a number between 0 and 9, but for example, if the model is unsure whether this is a 0 or a 6, it should be able to express that and not just return some number between 0 and 6, because this may not be useful for what we are trying to do with the recognized digits afterwards. And for image classification, it's very similar. Now, just in this case, we have a color image, so we can represent the input as a 3 tensor of red, green, and blue values for each of the pixels. And again, the output is a vector of class probabilities. For image colorization, again, we can represent the input as a matrix of gray values and the output as a 3 tensor of red, green, blue values. And for image generation, one possible scheme is to express the solution as a mapping from some random vector to an image, again as a 3 tensor of RGB values. That's just one way to formalize image generation, and that's one that's quite popular nowadays because of the generative adversarial networks. And for text generation, we can try to encode the input as some vector that represents the character that was given, generated at the last step, or in the beginning it would be some seed. And also we have a kind of internal state that we also initialize in the beginning, and then we ask the model to produce a vector of probabilities for the next character and another internal state, and then we insert this back into the model and kind of recurse so it can generate the text character by character. That's one way to formalize this. And for the boundary detection task, one way is to simplify the task a little and take as input just an excerpt of the spectrogram, a magnitude spectrogram. So this can again be expressed as a matrix. And the output would be a scalar telling the boundaryness at the center. So again, a value between 0 and 1. 1 if there's a clear boundary, 0 if there's no boundary. And once we have this function, we can apply this at every position in the input that we want to predict boundaries for. And we get a curve like this, and we can pick peaks in this curve to get the most salient positions of boundaries. So as you see, there's a lot of tasks that we can formalize in the way that the solution is some mapping from one tensor to another tensor. And this is actually a prerequisite for just solving these tasks with the computer in the first place. Now we assume that we are either unable or unwilling to specify this function fully by hand, and instead we define the function so that it has some free parameters. So it's a generic function that has some free parameters that can be adapted to get what we want. Then the next step is to define a loss function. The idea of the loss function is to return a scalar value, so it will return a scalar, and it should be smaller when the solution is better. So it tells how bad the solution is. And again, we assume that we are either unable or unwilling to specify this loss function by hand, so we leave some values to be filled in. In this case, it's the training data. And it usually takes the form of some sum of a penalty function over all the training examples. So the job of this penalty function here is to compare the output or the prediction of the model with some target value and tell how bad this approximation is. So this then is usually specified by hand, but it's a lot easier than trying to write down a loss function for all tasks. And finally, we try to optimize the model parameters to minimize the loss we defined. And how all this looks like depends on the machine learning method we choose, and we'll see what this looks like in deep learning in a minute. So this is are the core ideas behind machine learning. Now we'll have a look at deep learning again. So the formalization is always stays the same. Now deep learning is machine learning with a particular design choice, which is to make the model function a stack of many nonlinear operations, usually an artificial neural network. And all the rest in deep learning follows from this design choice. So artificial neural networks are not simulations of a brain, but just a name for a particular family of mathematical functions, which includes this function, which we can visualize as a graph. So it takes some input vector, computes a weighted sum, where the weights are the parameters of the model, adds some offset, and passes this through a nonlinear function, which could look like this. For example, this would be good for the muffin versus dog task. So you get whatever the input is, the output will be squashed to the range between 0 and 1. And this is equivalent to logistic regression now. Then we can have multiple of these weighted sums and nonlinearities. So we get a mapping from a vector to a vector space of arbitrary dimensionality. And we can also stack this. So we can take the output here and put another matrix multiplication and another offset and another nonlinearity. And the nonlinearity is always applied element by element. Now it's important that there's a nonlinearity in the middle here, because if there wasn't, we could just collapse the two matrix multiplications into one, and we would be back at this model. So this is what makes the model D. And there's a theorem that says this model here is already capable of approximating any function that has fulfilled some smoothness constraints. So for the tasks we have seen before, actually all of them would in theory be solvable with this model here. So why should we use any more layers than this? The problem is that to approximate a function well, you need enough units, and enough units could be a lot of units. There are some proofs that show that there are functions that can be expressed with a deep and relatively small network that take exponentially many units if you try to express this with a single hidden layer. So deeper functions can express some solutions much more compactly. And also the proof only says that there is a network that can solve the task. It doesn't tell how to find it, and it turns out that in practice, training a very, very wide network with a single hidden layer doesn't work as well as trying to train a deeper model to solve a task. So we're back here, we're adding another layer, and now this is a deep network. Now you see it's getting silly to repeat all these steps over and over here, because it's basically just a composition of the same function with different parameters. So we can write it this way. And now this function is what's usually called a layer in deep learning. In this case, it's a dense layer or a fully connected layer, because every output depends on all the inputs. And that's the way neural networks are usually modularized. So you have some prototypical layer functions and you compose them. Now deep learning dense layers are very great, because since every output depends on all the inputs, it means that the order of inputs doesn't really matter for the learning problem. If we swap two of the inputs, then the task will stay exactly the same. So for example, if we're trying to distinguish some flowers by some measurements of the blossoms, we only have to decide in what order we want to present these measurements, but we don't have to optimize this in any way. It doesn't matter if we present it in this order and this order, as long as we do it the same for every data point. And actually the same also holds for the targets, so we don't have to decide in what order we put the targets. And that's great. Let's look at another task where the input is encoded as a matrix. Again, since the output depends on, each output here depends on all input pixels, we can just swap two pixels or just permute all of them, and the task doesn't change at all for the network. But you see it becomes quite impossible for humans to distinguish the numbers here, so maybe we're missing out on something. And to make a long story short, what people are doing for this kind of data is to use convolutional layers. So instead of having the inputs be scalars that are multiplied by scalar weights, we have make the inputs be matrices that are convolved with matrix weights, or higher order tensors. If you have higher order, if you have volumetric data, you would use 3D tensors and 3D weights. And then the rest is the same. You sum up all these elements and apply an element nonlinearity, and then you get the output. Now what's the consequence of using this instead of dense layer? Since the output now, each output now only depends on a small local part of the input, it does make a difference now whether you permute the input pixels. And also the output still retains the spatial layout of the input, so this means you can stack these kinds of layers. And since the weights we have here are usually much smaller than the input matrix, so often they are just, for images, they are just 3 by 3 pixels. You can process a large input image with just a few weights. And those weights are required to be applicable at every position in the image. So this means the model is forced to learn some features that are generally useful to process images. And there's a second layer that's commonly used, since now we potentially get a lot of images from a few input images or a lot of pre-processed versions. We possibly could get an explosion of data, and one way to deal with this is to downsample the data again. So this max pooling layer would produce some grid over the input image, and for each patch only keep the maximum value. Or you could also do average pooling, where for each patch you keep the average value, but max pooling is more common. So these are the ingredients for a traditional convolutional network, which looks like this. You have some at the input, you have some convolutional and pooling layers. The convolutional layers extract some local features. The pooling layers reduce the amount of data and also introduce some input translational invariance. Because most often when the input is just shifted by a single pixel, then the maximum within the patch will not change. And finally, in the end, if you want to have a single prediction for the input image, like telling whether this is a muffin, you will put some dense layers that integrate the information over all the input positions. So that's what a traditional company looks like. And with the same building blocks, we can also produce models for other tasks, like for digit recognition. The only thing that changes is that we would have 10 outputs here instead of 1, and a different nonlinearity in the end that ensures we get a vector of class probabilities. And for the colorization task, this is a bit special because we want the model to be able to process input images of any size, not just a fixed size, and then produce an output that is the same size but in color. So what we would do here is to only use convolutions and not a dense layer that tries to produce a fixed size output. Alright, so now we've seen how to build models in deep learning, and the next step is to define the loss function, which boils down to defining the penalty function that compares the prediction with some target. So for the binary classification task, this is something that mathematicians have come up with and I don't understand. So for binary classification, the common loss function is the binary cross entropy. For categorical classification, it's the categorical cross entropy, which has some logarithms in there. And for the colorization task, so imagine this is the output by the model, this is the ground truth. Possible loss function would be to compute the squared difference of each direct green and blue value at each position and just sum up everything. So you get the squared error. That's also would also be the loss function of choice for the concrete cylinder task. So now we have everything in place. Now we just need to optimize this to find the parameters that minimize our loss. And in calculus, you learned that you would take the gradient of the loss function, set it to 0, and solve for the parameters. This doesn't work for these kind of functions because they are non-convex and very complicated. So what we can do instead is to employ some iterative and numerical optimization scheme where we initialize the model parameters randomly, then we figure out in which direction the loss decreases, and we move the parameters a little bit in this direction, and then we repeat until we find some minimum. Now, how do we find the direction in which the loss decreases for a deep model, for a neural network? So now I'm going to explain backpropagation in a very mechanical and engineering way. Let's see how this turns out. So imagine we have the digit recognition network, and it says, okay, I think this is a 0 with confidence 0.6, and maybe it's also a 2, or maybe it's 6, maybe a 9. And the target we have here, the outcome we would like the model to produce, assigns 100% to the 0 and 0% everything. Now, let's first blow this up to make explicit that we actually have two operations within each of these layers. We have a linear operation that depends on the weights, on the parameters we're trying to learn, and we have an element-wise nonlinear operation, both for the convolutional layer and for the two fully connected layers. Here I skip the fully connected layer again. Oh, yeah, I missed this slide. So mathematicians have ensured that the nonlinearity we used here, in this case, it's the one that produces class probability vectors, and the loss functions that I introduced before match up in a way that in order to decrease the loss, we have to modify the output of this last linear operation in the direction of the difference of the target vector and the vector it produced, the model produced. So this is the direction we need to move the output. So, and since the output has the bias added to it, this is also the direction we need to move the bias. Very easy. And for the weight matrix, it turns out that we need to move it in the direction of the outer product of the input we get here and the direction we want to change the output. So we have the input to the layer here, which could look like this. We have the direction we want to move the output, and now we figure out, okay, we want to move the output, increase the output here. It pays off to increase it a lot where the input is large. It doesn't matter whether we change the weights when the input is 0, so at this point we do nothing. And we basically just multiply all these numbers and we know in which direction to move the first column of the weight matrix. For the second column, where we don't want to change the output, we don't change the weights at all. And if we want to decrease the output, we make this weight smaller because all the inputs were positive. Alright, so this is basically the gradient of the weight matrix. Now the gradient of the loss function with respect to the weight matrix. But I'm going to the technical mechanics to explain what this looks like. We can do this for all the columns, so we get the direction we need to move W3. Alright, now, so this is basically kind of computing the correlation between what the input was here and what we want to change the output to. So it's strengthening the connections where both are large, and it's weakening the connections where they disagree. And that's the direction the loss decreases. So now how do we do this for W2 and W1? Well, for this we first need to know in what direction do we need to change Z3 and Z1, the output of the two linear operations. And in order to do this, note that every block here is a mapping from some tensor space to another tensor space. So what we do now is we replace each of these mappings by a linear transformation that quantifies, or a matrix that quantifies how the output changes if the input changes. And these matrices are the Jacobians of these functions. So that's the generalization of the gradient for multi-dimensional input, multi-dimensional output functions. Now for J6, this is kind of easy. So we want to find the matrix that tells us how the output changes if we change the input by a small amount. And since the output is just a weight matrix multiplication of the input plus some bias, it turns out that the Jacobian we're looking for here is just directly the weight matrix. And that was basically just taking the gradient of this function with respect to the weights. So now we can use this Jacobian in the other direction as well. So we know what direction we want to change the output, and we can multiply it by the Jacobian to know in what direction we need to change the input to reduce the loss. And we can do this for, we have to do this for the next Jacobian here as well. This one is for the nonlinear operation. And the nonlinear operation is element-wise. So every input we get here is passed towards nonlinearity separately. So we know that the Jacobian that quantifies how the output depends on the input must be a diagonal matrix, which has only non-zero entries in the diagonal. And the nonlinearity looks like this. For example, it could be a sigmoid function. So how does the output depend on the input? It depends on the input. In this case, if the input is 0, then the output, the magnitude the output changes will be about 1/4 of how much the input changes, as long as we only change it by a little. If the input is very large, either positively or negatively, then the output doesn't really change at all if we change the input by a small amount. And if it's somewhere in between, then the dependency is somewhere in between. And luckily, some famous engineers like Fermat and Leibniz and Newton, they figured out how to quantify this exactly. So this is the derivative of the sigmoid function. So this is what we have on the diagonal of this matrix here, of this Jacobian. And now again, we can use it in the other direction to figure out how we need to change Z3 to decrease the loss. And we can do this for all the other Jacobians here as well. So now we know how to change Z3, and for Z1 we have to multiply it by all the Jacobians that come in between. And I didn't talk about how to do this for these two things, these two guys, the max pooling and the convolution. And in this case, the Jacobian is a high-order tensor because the input is already a matrix and the matrix output as well. So I will not discuss how the Jacobian looks like, because actually we never need to compute the Jacobian. All we need is to multiply the direction we want to change the output by all these matrices. So we only need to know how to multiply a gradient by the Jacobian. In this case, for the max pooling layer, remember that the output is just taking the maximum position, maximum value in each input patch. So it means the output here, this 3, only depends on the maximum here. This 5 only depends on the maximum value here. So if we want to figure, if we know how to change the output, let's say it's A, B, C, D, we copy this information back to the maximum position in every input step. And now mathematicians will tell us that so this is the gradient of the max pooling operations. And mathematicians will tell us that in this case the gradient is actually undefined. But we are engineers, so what we can do is we just copy it to both positions, or maybe we just copy it to one position. That's considered in an engineering decision. That's you can do it either way. It works. Because also this situation doesn't happen very often in training, so it doesn't really make a difference. Then finally for this Jacobian, notice that the forward pass is just some convolution of some matrix with a smaller matrix that gives us another matrix. And it turns out if we know how we want to change these outputs, we can, there's a funny sign here. We can so this should be the nabla. Anyway, we can compute the direction we need to change the weights and the direction we need to change the input, also just by applying convolutions. That's very convenient because we only need to implement convolutions efficiently, and then we can also use it for the backward pass. Okay, and the key thing is that this still both depends on the weights we have here. This will be important later. So what I explained here in long words is basically how to compute the gradient of the parameters, the negative gradient of the penalty function with respect to our parameters. And I tried to explain this more technically and tried to make it seem a little more ad hoc, because it's not the only way we can compute a direction to decrease the loss. So engineers have hacked this a little and still got away with it. And now note that this is only for a single example. This is just the penalty function for a single example. If we want the direction for the whole loss, we need to sum or average this over all the training examples. So then we get the direction we need to change the loss. And then we can start our optimization. So just a toy example with 2 parameters, 2 weights. So we start by initializing the weights somewhere randomly. Then we figure out which direction locally the loss decreases. And then we move a little bit in this direction. Then again, we figure out in which direction locally the loss decreases. And we move a little bit. And we move a little bit. And we go on like this until finally we end up at the minimum. So this is how deep learning works. So we've seen how that we need to formalize the task, and we can define the model in some way of the building blocks we have, the layers we have. Then we define a loss function. This is usually pretty much set, but there's also a lot of room for doing tricks there. And then we optimize the model parameters, so minimize the loss. So that's how deep learning works. At least in theory. In practice, we have to do a lot of things differently from this. The first thing we'll look at, the first issue we'll look at is optimization. So what I explained here is a very nice example. It works very well, but it's a fake example. It's sad. So the first, let's first review this step to see why optimization is more difficult in practice than in the toy example. Remember that in order to find the direction which the loss decreases, we start with just taking the difference here. This tells us how to move the output. So for the output, we know directly how to change it. But for the earlier layers, up to here, we have to multiply this direction by all the Jacobian matrices that come in between. One source of problems is the nonlinearity. So it's in this matrix. So as we've seen before, the values in this Jacobian are the derivative of the sigma, and if we have very large or very small inputs, then the derivative is close to 0. So it means that the Jacobian, or multiplying by the Jacobian, will basically remove any information we have about where to move. So any of the earlier layers will not know in what direction to move anymore, neither for the outputs nor for the weights. And in 2012, the AlexNet paper popularized another nonlinearity, which was invented before, but this is what made it really popular, or showed that it really works, which is to simply clip all inputs that are below 0. So for this function, the Jacobian entries will be 1 when the input is greater than 0 and 0 otherwise. So there's no squashing taking place anymore. And in practice, this works a lot better than using sigmoids. So this has basically replaced all the signals in hidden layers. Then the others, which are not the nonlinearities, are the matrix multiplications here and the convolution here. And the Jacobians here are directly the weights. And the Jacobian here is a very complicated tensor that still has the elements of the weight matrix of the filter kernel spread around everywhere. So the key thing is that these Jacobians depend on the weights we have. Now the problem is, depending on how the weights are set, the information here in which direction to move may either become very small, if the matrices here between have very small values, or smallish values, which is called the vanishing gradient, or they can become very large, which is called the exploding gradient effect. And this all depends on the parameters we have. So we need to review this step more carefully. We can't just take any random initialization. We have to be very careful how we initialize the weights so that we get meaningful gradients afterwards. And in 2006, Hinton invented or published about a technique which is to initialize the weights with unsupervised training with restricted Boltzmann machines in a greedy fashion, layer by layer. And afterwards you can fine-tune the network with the backpropagation mechanics I explained before. And in 2010, Gloro and Bengio figured out, well, we could also take random weights here and everywhere, but scale them in a way that they would preserve the variance of some hypothetical Gaussian input data when it's propagated through the network, and also preserve the variance of some hypothetical model distributed gradient if it's propagated to the network in the other direction. So this is just a simple formula on how to scale the weights. Then in 2014, Sachse figured out, okay, this kind of works, but if you look at the singular values of the Jacobians you get by this, while the multiplication by the Jacobian preserves the variance overall, if you look at the singular values, there are some values that are very few values that are very large, and all the others are very small. So it preserves the variance by emphasizing the variance along some of the eigen directions and squashing the variance in all the other directions, which is probably not very optimal. So he proposed to initialize the weights as random orthogonal matrices instead. And then later in 2016, some people proposed, well, why do we do this all just mathematical and theoretically? Why don't we figure out the scale based on the actual empirical data we have? So we propagate the data until it reaches the weight matrix we want to initialize, and we figure out what's the variance of the data, and we scale the weights so that the variance becomes 1. So this is a scheme that was proposed by 3 different papers almost at the same time. And it also works. It means it works no matter how what kind of network architecture you have and what kind of nonlinearities. But what's most commonly used in practice is still this one, because it has a simple formula that depends on the number of inputs and outputs, and that gives you the scale you need to initialize your weights. All right. So we have fixed this step. Now let's look at this step again. This is also problematic. As I said, this scheme here is just for the penalty for a single example. And to get this for the full loss, we need to do this for all the examples and average over them or sum over them. This is very expensive. So what we do in practice instead is just to take a small random subset of examples to find the direction. And we choose a different subset for every update step. So now this works as well. Let's consider this step. What I explained before is called stochastic gradient descent, where we compute the gradient and then we take a small step in the direction of the gradient. Now the question is, how far should we move? Let's imagine we are in a parabola and we start somewhere here and we want to find the minimum. If we set the learning rate, this factor here, too small, then we only make very little progress along this line. If we make it very large, then we start oscillating, or maybe we even jump out of the valley. So we need to set this learning rate correctly. And in this example, it's easy to find a learning rate that works very well. But if we're in a high-dimensional space, we usually don't have the same slope in every direction. So this is the Rosenbrock function, which has a very steep edges along this side and almost no gradient in this direction. If we make the learning rate small enough so that it doesn't oscillate here, then we make very little progress here. And if on the other hand we make it large, then it looks a little bit better, but now we're almost risking to jump out of the valley again. So what people are doing instead is to use stochastic gradient descent with momentum, where we keep some velocity that is updated. So it's like the analogy could be a ball that rolls down the hills, and it's accelerating in the direction of the gradient. It has some friction, and then we move the parameters in the direction of the velocity vector. So this way the oscillations are damped a little bit and it builds up momentum in the direction of the valley here. But it still oscillates. So another very popular scheme nowadays is Adam, which also has this velocity, the exponential moving average over past gradients, but it also has exponential moving average over the past gradient magnitudes with a much longer history. So this scales the learning steps so that directions in which the gradients are always very large are scaled down a bit, and directions in which the gradients are very small are scaled up. So this gives a very smooth progress here. And it also works well in the kind of problems that are encountered in practice. Okay, so we're getting better and better. But now that we move the parameters away from the initialization, we break things again. Remember that the gradient always depends on all the weights we have in between. And if we change the weights, then there may be getting the vanishing or exploding gradient again. And one way that engineers solve this is by clipping the gradients. So at this positions here between the layers, we scale or clip the gradients when they become too large. This means we don't really follow the gradient of the loss function anymore, but it seems to work in practice. Or another way is to parameterize the weights such that we don't only initialize them to orthogonal matrices, but we parameterize them in a way that they can only always be orthogonal matrices. Or a very common hack is to introduce another operation between the linearity and the nonlinearity that just scales the input so that it has unit variance and zero mean. And we compute the statistics for that based on the current subset of data we use to compute the direction of the loss function. After training, we fix these statistics. Okay, so now we fixed all in optimization. Let's get to the elephant in the room, which is generalization. So what we did here is we carefully optimized all the parameters so that the function will give us some output that is very close to the target output for every input in the training data set. But that's not actually what we want, because for the training data we know the output we want anyway. We don't need a function that tells us what the output is. What we actually want is a function that gives us a prediction close to the true output for all data points that are not in the training set, but come from the same underlying distribution. And the problem is that there are very many, I guess there are infinitely many, of course, solutions that only fulfill the first criteria, but not the one that we want. And it would be very lucky if we got one that we wanted just for optimizing the function to reproduce the training data. So, for example, if we have a 1D regression problem where the input is one-dimensional and the output is one-dimensional, we could have a function that carefully reproduces all the training examples, which are not included, but does a weird stuff for inputs outside of the training set. And this is called overfitting. That's a general problem in machine learning, of course. And our goal is to modify the optimization in a way that we avoid such solutions that only match the training examples. And these are, again, many engineering tricks. So one way is to observe that in order to learn all the training data by heart, the function occasionally needs to make some large jumps, which means it will have a large gradient with respect to the input. And the way we define the functions, this can only happen if there's a large multiplicative interaction of the weights with the input. So in order to rule out such solutions, possible measure is to shrink the weights after each update, or clip them whenever they get too large or their norm gets too large. This is called weight decay. Another idea is based on the observation that the training is iterative, and in the very beginning, when we have random initialization, the model probably underfits the training data, meaning it doesn't reproduce the correct answers for the training examples. And at the end of training, the model overfits. So somewhere in between, there should be some sweet spot, which is before we have all the models that underfit, afterwards we have all the models that overfit, and in between there should be a model that neither underfits nor overfits. And we can monitor the loss on an extra data set that is not used for optimization to find the sweet spot. And then another observation is maybe sometimes in order to learn training examples by heart, the solution will use some properties of the input that we know are not relevant for the task we want to solve. So for example, for object detection, if we just want to detect whether there's a cat in the picture or a dog or whatever, we don't care whether the cat is facing to the left or to the right or looking upwards or downwards. And some possible solutions for this are to just use more training data, so the model will learn about these invariances, or actually try to make the model so that it cannot use the orientation. This may be very difficult. And another way is to use data augmentation. So we transform the data in ways that we know are relevant and hope that the classifier will learn to ignore these transformations. So basically we are introducing some stochastic transformation in the beginning of the network, which for images could include like horizontal flipping or scaling or changing the rotation or the colors, but it all depends not only on the domain but also on the task. For digit recognition, it doesn't make sense to do horizontal flipping, for example. And for audio, it could be time stretching or pitch shifting or applying some equalization that changes the frequency curves. Then there's dropout. This is based on the observation that units may learn to focus on only very few units in the layer before in order to distinguish the different training examples. And the solution is to just drop half of the units during training and choose a different set of units for each training example and scale up the surviving weights to compensate for this loss. So again, this will introduce some stochastic layers that basically just multiply the input by a binary mask. And in the backpropagation mask, they also multiply the gradient by this binary mask. And at test time, we don't do any dropout and also don't scale up the weights. And this can be interpreted as training an ensemble of 2 to the n networks, where n is the number of units that could be dropped with some shared weights. And yeah, just to see what the effect is, if we train a digit recognizer, it will push the model towards learning more stroke-like features that depend on many input pixels that are usually correlated in the data, because this makes the features more robust to possible dropped pixels, and also changes the training curves so it doesn't overfit as much. Okay, so this was optimization and generalization. These are a lot of engineering tricks, but usually all of these tricks that I mentioned so far are used together for state-of-the-art deep learning models. Now just a short view on more architectures. What we've seen so far are just simple stacks of convolutional and pooling and fully connected layers. But there's a huge design space in how to design the neural networks. One question is, how many layers should we use? We've seen that 2 layers or a single hidden layer is enough for the universal approximation theorem. But if we have more layers, then we can express some functions more compactly. And if we look at the results for the ImageNet classification, which is an object detection task, we see that in 2012 the best solution had 8 layers. 2013 it also had 8 layers, but it changed something in the layers, how large the convolution kernels are and things like that. In 2014 the best solution had 22 layers. In 2015 it had 152 layers. So you can see some trend there, which is to use a lot of layers. And it seems nowadays that it's not always the best way to just use as many layers as you can. But still, we should probably use more than just 3 or so. And now the question changes a bit, how to use many layers. What GoogleNet did was to introduce some auxiliary classifiers. So the problem is, even if you initialize all the weights nicely, it's still a long way to go to get the direction we want to change the output through all of the network. So what they did is they added some additional branches here that are also trained to predict the correct target. So we have some gradient coming from here and from here and from here. Then there's the ResNet, where the idea is to introduce some skip connections, some bypasses, so that basically the output directly depends on the input to the final classification layer, and directly access the input, and all the layers in between learn the residual errors that are made. So the transformation these 2 layers do is added on top of the original input. And this was shown to be able to train networks of 1,000 layers, but it was also later shown that these networks do not really behave like very deep networks, because most of the time only very few of these residual blocks contribute to the output for a particular training example. So it's more like an ensemble of shallow networks, not a very deep network. And there's DenseNet, which is very similar to ResNet, except that the shortcuts don't add the features to what was there, they append it to what was there. So each convolutional layer here would append a few feature maps to the collection of feature maps that was already there before. This means the final classification can depend both on low-level and on high-level inputs. And this avoids having to relearn features at multiple stages in the network. And then another dimension is, so we have the depth of the network, the number of layers, we have the width, which is how many units to put in each layer, and then we have the multiplicity, which is how many independent computational paths to use in the network. It can be advantageous to have some separate computation paths that are not allowed to exchange information in between. So AlexNet already did that with two separate paths that are structured the same way. And he only did that for a technical reason because he wanted to put these two paths on two different graphics cards without any communication between them, so you could train the network faster. But it was later shown that this also improves the results. Yeah, it was shown that so he already put this in the paper, maybe you know this figure, but what's interesting is that these are the features the first layer learns for the one of the paths. These are the features for the second path, so this one seems to learn more shape features, and this one learns color contrasts. You can imagine if you increase the multiplicity, it may learn more separate feature sets. And there are papers that try to explore this dimension in addition to the depth and width. So this is an interesting take that starts also from the idea of having separate processing chains. So this is the residual path, this is the bypass connection. And then there are two parallel computations that are averaged in the end, but only at test time. At training time, they sample some random value between 0 and 1, and then they choose a different weighted combination based on this random drawing. And now what's the actually interesting part is, for the backward pass, they sample another random value between 0 and 1, and then assign the gradient based on these randomly chosen weights. So it completely messes up the backpropagation. It doesn't compute the gradient of the forward pass anymore. It just chooses some random way to distribute the blame onto these two computation passes. And this is, I think, still the state of the art on Cypher 10, which is a small image recognition dataset. This is just an example to show what you as an engineer can do when you just break apart the backpropagation mechanics and try to find other ways to find the direction to decrease the loss. Okay, so these were the architectures, and the final step, I guess it will not take long, is about inspection. So we now have a nice network, or assume we have a network that is very good at, for example, object detection, and it can take this input and tell that there's a king snake in the input. Now we want to know why or how does it work, because otherwise it's just for now it's just a black box that gives us the correct solution. And a simple way is to visualize the filters, but this only works for the first layer, where you can directly visualize the weights in the pixel space. Another way is to find training patches that maximally activate a specific unit. So for the unit here, these are some training patches that maximally activate the unit. And we can do the same for all these. So here we have something that detects a particular oriented edge And you can see this oriented edge in all the training patches that maximally activate the unit. And we can do this not only for the first layer, but for all the later layers as well. So we see that later layers learn some more structured, or also edges, or something that looks like keys, keyboard keys. And for even higher layers in the hierarchy, you see something that detects spectacular lightning, and some that detects dog faces or keyboards. And this already gives us some insight on how the network is processing the data. And another way is not to find the patches that maximally activate some unit, but generate data that maximally activates some unit. So you start with some random input, and you compute the output, you compute the gradient of the output with respect to the input, and you modify the input step by step to maximize the activation here. And you also apply some averaging in between, so you enforce some correlation between neighboring pixels. So this makes it look more like images. So you see this is what makes the network think they are gooses. This is huskies. It looks very edgy, but it is also the same technique was used for this Google Deep Dream trick. And another way is to compute the gradient of some unit with respect to an actual training example. So it's the same idea as before, but instead of computing it for a random input and modifying the input, we take an actual example, training or test image, and we compute the gradient of the input with respect to the output. So this tells us which pixels are affecting the prediction the most. And in this case we don't really see it very well here, but it actually figures out or tells us that it predicted the snake mostly because of these pixels that make up the snake. And we can do the same for audio as well. So here this was for singing voice detection network. This is the input spectrogram. It's very dark, but you can see that the input highlights the spectral bins that make up the voice, and you can also listen to this afterwards and see how well the network reacts to the voice and to what else it reacts in the input. Okay, so this also closes inspection, and that makes the picture complete. So in conclusion, deep learning is something that, well, that's a meme that's common in engineering. If it looks stupid but works, it ain't stupid. Thank you.